Welcome, everybody. Uh, I hope you're relaxed after all the week. Hope you had already lunch because the breaks are not very long. And after all the week, I hope I will not bore you to death. So I'll try to make it fun and reactive. From the people who are here, how many of you have heard about reactive concepts and started to experiment it or at least study the concepts? So around half of you. For those who don't know or didn't come to reactive concept, I hope you at least have the idea of how threads work and what might be the target or goal for reactive concepts. But I'll also explain in the beginning what is the idea behind it and what is the advantages. Later I will come back to some of the disadvantages or complexities, let's say. So here's some info about me, but I don't want to bore you to death, so just make it quick. I'm a PyR engineer and my background is Java EE. That's the most important part of it. And I'll present you 5 different steps which build one on top of on the other, how you can improve your current applications with a reactive style. So I'll not be speaking about building new applications, which is also possible with Java EE, but you have many options out there. Some of them are much better for reactive programming from the start, but they also force you to use reactive programming to some extent because they only expose the API, which are asynchronous, and maybe it's like it will take some time for you to understand the API and how to use it effectively in every part of your application. But now I'll be talking about a legacy application, or legacy is maybe not a good term, but your existing applications which you want to evolve or you started work with and now you see you need to improve it because it's lacking in performance. So I'll present steps on a real big application, what can be improved what can be changed on the application to improve it in performance. But to start with, our applications are usually like this. Again, boring thing. You get a request, process it with some logic, wait for resources, and at the end, when you have all the data, you send the response back. In most cases, this is quite natural, but if resources are slow, you access database which takes long to get the data from, or external resources, what happens? What do we do first? We simply wait. Because that's what we do with calls to database. We wait for the response, and then we continue happily with processing. But the problem is that it may take long, and other requests are coming. So in most cases, it works well, but in some cases, when you have high load on the application and the resources are slow, you get to something like this. You starve your application or starve the request processing because there are no more threads, no more resources to process the request because all of them are busy. And busy doing what? Busy waiting for other resources. So there's a lot of overhead in waiting. All the threads that call database or call external resource are just there, consuming some memory, consuming some CPU load when you want to switch threads. But in the end, most of the time you have a thread pool, and the thread pool can be exhausted with all the threads waiting for some resources. And new resources just need to, new requests just need to wait for these threads. So the application basically stops responding to more resources, requests. This is just all the things that may happen in your application. And first you have waste of resources, slow application processing, and even in case of failures, the client, the one who requested some data from your application or the service or a user, will find out that something is wrong only after these all resources stop to wait and continue processing this request. And that's awful lot of time to just find out that the request, that something was wrong in the request and I need to restart the request. And what usually people do when they wait, they start the request again. That's what normally people do. With automatic services or just services which are not users, you can also have some retries there. And all these retrying will again consume more and more resources because it's the same thing again and again. And if one is waiting, all the others will wait. So we want to focus on getting rid of these problems. And here is where reactive approach may help. Reactive Manifesto is an initiative by some clever people who wanted to solve this problem and realized that there has to be some other approach than the standard blocking approach and running everything in one thread. And at the same time, they wanted to make easy to do parallel programming. So it's not like you have to manage all the threads and somehow synchronize between them. You would want to just pass tasks to these thread and then pass the task not to another thread and make some framework or some executor do sending these tasks to proper threads which are not busy and can process your request. And the Reactive Manifesto just describes how this can be done and how the application should be built to respond in case of failures, in case of high load, and also first and foremost, which is up there, to be responsive to user interaction, responsive to any problems, and also make it elastic so it can respond to high load when too many people or too many services access your application. And at the bottom of it, the core concept is being message driven. So if you build your application asynchronously by passing messages among components, that's the main concept to make all this happen. It's not the only thing, but it's a good solid base you can build on and build all the solutions on it. Now I'll explain how reactive programming helps with thread starvation. Initially, when we have a request processed in a single thread, which is a traditional way of processing requests in application servers or even in frameworks like Spring and other frameworks, everything runs in one thread, and when you need to access external resources, you need to wait. In our terminology, technical terminology, we say we block execution. So on the left, we have incoming requests. All the red blocks are when our threads are waiting. On the left side, we have traditional way of processing requests where the thread is blocked also when there is waiting. And we want to reach the scenario on the right side when threads are released. So they are only blocked in these blue squares. And what we need to do is to execute a request for resources for data in an asynchronous way so that when the request is finished, our application is called back. And the callback can be executed on a different thread. So basically the request processing jumps from between threads and is only triggered when there is some data we need to wait for. We need to have to continue the request. And you may see that in the end, once more, in the end, you block threads for much less time. So when there is another request, it can reuse the threads that are that are released. And in this example, normally you have 2 requests and they would consume 2 threads. But in the end, when you just sum up the time consumed by these 2 requests, it's even less than 1 thread. So even some requests could be filled in. And if the gaps are not big enough, it would take a little longer time, but still 1 thread, because the task would need to wait for the other task to stop, to finish, but not to finish for the complete execution, but only the piece of code that can run until another data is requested from an external resource. Then the thread is released and can be reused by other requests. So that's where we save resources. And also, if we add another concept, which is responsive sending of messages back to the user via synchronous messages, then we also can inform the user between the database calls or external calls, and inform the user or the client that there is something going on, that we already have the data from this resource, but we need to process another resource. And in classical UI, you would probably update the data you receive, or just increase the progress bar so that the user knows what's happening and they will not restart the request. So I want to also show you some code. So I'll take a big application created by Java EE evangelists at Oracle to demonstrate features of Java EE. So it's not just a small Hello World application, but it represents maybe one of your applications you already work in your daily job. And on another side, in some series of steps, I'll focus on one thread of execution and try to show you how we can improve it with this reactive programming in Java EE. What happened? I clicked on the link accidentally. Yeah. So first concept is a synchronous API. You certainly need some synchronous API to make this possible, because normally APIs are blocking and there's no way around it. If you execute a call and wait for a method to finish with the data from external resource, then there's no way to really work around it. You just need to wait there. But if you have a synchronous API which supports callback, passing a callback, then you can execute a call and then continue execution, because the method returns immediately. It will call your callback when the execution is finished, and usually it will be in a different thread. So you can continue execution. If you need the data during the execution, you can still wait for the other thread, but there are other options to simplify it or to make it more efficient to just use one thread all the time. Java EE provides many asynchronous APIs. There are some which are missing, mainly because they are based on Java's base, or Java standards, which are just in any Java application. Which is one of them is JDBC, which is a standard to access database, and JDBC itself is not part of Java EE. It's part of the language. It doesn't provide means to access data from a database asynchronously. If you want to access data from a database asynchronously, you need to have a synchronous driver, and this is not covered by JDBC. You need to have a synchronous JDBC or something like that. There's, I know from Oracle developers that they already work on another standard for asynchronous JDBC to support this, but until then, there's really no way around it. Some databases provide their asynchronous drivers, so you can use their Java bindings. Like MongoDB, I know that they provide asynchronous drivers, but this is not part of the standard, so it's different across databases. What's cool that for REST invocations, you can use the asynchronous client. So basically, one of the options may be to extract the database calls to another REST service running on different processes so that it doesn't affect your main application, and then access the data from this service. But this is quite a lot of overhead, so I'll come back to this later and explain how to solve this. So the idea with these asynchronous calls is to improve this straightforward processing with to get some response faster and also release the thread during the request. As an example, I'll focus on one request in the application. I'll show you the application in a couple of minutes. The request is processed just in one pipeline through multiple layers, and in the end there is a REST call to another service that will just provide some data, and then it has to bubble again to the XHTML file, the JSF file, which completes the response and sends it to the browser. This is what very often you do when you don't think about optimization. And it's quite a readable code, so it's quite natural to do. What we want to do is to execute the REST call and immediately continue processing further. So one thing we could do is to immediately respond something to the browser that the request has finished and we need to wait for the data. So the user knows that something is being working on. The initial thread is released, is not consumed, and when the REST service is finished, the REST call is finished, then the data are sent back. The one more complexity, let's say, is that we need to update the browser, the same page. So we need to use some asynchronous method like WebSocket, which I used in my demo. You can use server-sent events or just AJAX polling for some data, but server-sent events and WebSockets are better because they are naturally asynchronous. You can update the data from the server to the browser without any fuss. So to show you the demo application, no. Where is it? Here. The cargo tracker application is quite a simple application. There's lots of details, a lot of things are happening at the bottom, but to understand it's pretty simple. It's an application which tracks packages which normally people want to send from one part of the world to the other part, and the cargo delivery company basically runs this application so that people can see when they get the ID of the package they want to send, they see where it is, how long it will take to come to the destination. And also, the application also has an administration interface for the delivery company, where they can see which packages are scheduled, which are not scheduled, and somehow plan the delivery. One of the features is to schedule routing of messages. You saw I clicked the link, but it took quite a long time to load the page. Because the page in this simulation is obviously delayed, but in real world it would be delayed by getting data from database or from some service that needs to process all the possible ways to route the cargo from one town to another town, and there are quite many combinations. So the service will provide some candidates that the package company employee can choose from, but these would all of them would work. It's just maybe some of them will take longer, some of them would be cheaper, and like that. But the downside is that it may take long, and you saw already that nothing was happening until the page was loaded. So that's the default state. We want to achieve something like this, at least with the first step. I clicked the same thing, but I immediately got a response. And then the computation is going on in the background, and the data is sent using WebSockets to display the data. So it's a bit of an improvement. The delivery company employee sees that something is going on and they need to wait until the data comes. There may be even a better improvement if the browser displayed all the candidates one by one, once they are available. Here, there are two updates. One is to receive initial information that something has started, and at the end, the data comes. But it's also possible to send each computed candidate one by one, so that the response time is even slower. Maybe the cargo company employee just wants to pick the first one, and they don't want to wait for the rest. And it again saves time, and the application is more responsive to what the user wants. So to achieve this, there are no, where am I here? There are more things we need to do. First thing is to prepare for an execution pipeline so that we can repeatedly process messaging or process the result of the computation and send them to the browser. We need to create an asynchronous pipeline, which is basically chain of callbacks. One callback is to receive data from the REST service, and then it sends information to another callback, which sends the data to the browser every time there is an event. And to build an asynchronous pipeline with plain Java 8, you can use Computable Future. There are other options, more clever options, but you need libraries like RxJava to do that. With Java 9, there is also another new API called Flow or Flowable, which comes from Reactive Streams initiative, but it's maybe not what you expect. It's more APIs, more complex way of doing things, just to give you more control over how the events come and how they are processed. But with Computable Future, you can start with quite easy, readable code and just call methods like then accept, then apply, which will accept a callback. And you don't have to nest your callbacks inside. You can chain the callbacks so that the code is still quite easy to read. And the difference might be as simple as this. This is on the left is the original code of the application. And to make just this component, there's obviously more components which we need to refactor. But this is the core component that sends data to the request to the external service, but doesn't have to wait, doesn't block the thread with this Computable Future and Asynchronous API. And the key to get this running is with JUX-RS, which is a standard of Java EE. If the application initially uses it to access the data, we can just add a call to async. So the API already supports synchronous calls. With new Java E8, there's another call called Rx, which immediately gives you a result of Computable Future until Java 8. So with Java E7, you still have to pass a callback to a get method. So that's another difference. Here, you just pass the type you want to receive from the get method, but the get method is blocking, so it waits there until the call is finished. Here, the get method returns immediately, and you have to pass a callback so that the server, the API, knows what to execute when the data is available. And another thing is that you want to have a result type of completable future or completion stage, so that you can easily build this asynchronous pipeline and chain asynchronous invocation without making the code really hard to work with and hard to use. I can show you how this would be with the new Rx in Java E8. So instead of calling async, we could call Rx, and then we basically can get rid of all the boilerplate, which is the callback, and we immediately get a completable future. If we want to do something with the result, we just call I don't have the Java E8 package, so it doesn't autocomplete, so I'll just improvise. Then accept, you get the value, and then in the lambda you can here is transit path, so you get the value of transit paths, and you can simplify the code, so that there's really only your code plus then accept method, which changes your code until after the asynchronous execution finished. So this basically is executed in a different thread. It seems like sequential, but with this completable future result and then accept method, the lambda is only stored and it's triggered after the execution is or after the data is available. So when you call something here, do something, this do something will happen before this lambda. The code in the lambda will wait until the request is finished. No, here. Do you have any questions to this? All clear or nothing clear? I guess. I hope I'll explain better later. Although this is getting more and more advanced. So if you have some questions later, which you're shy to ask, then come back to me after the talk and we can discuss. So as I explained earlier, another big concept in asynchronous and reactive programming is messages. You basically need them if you want to build your applications that are scalable and that are also responsive, so that you can send messages frequently without waiting for all the computation finished. And that's what we want to do in the next step. There are some options in Java EE. We already saw how WebSockets can be used to update data in the browser. You can also obviously use WebSockets between two Java services. You don't have to send it only to the browser. And there are also CDI events, which traditionally or normally by the standard, they only work within one application. So it's fine to build an application if you don't want to scale it, to build CDI events. But if you want to scale the application and send messages across different nodes, different instances of your application, or you want to send the events to different applications, in case you have a microservices architecture where every service does something in a different way or provides a different logic, then CDI events wouldn't work out of the box. But it's quite easy to use a plugin to listen to CDI events in your application, send it across the network to all the other recent listeners. And this is what one of the implementations of Java EE called Pyara provides out of the box. You basically can build it yourself, but if you want to just experiment with it, you can download Pyara. It's open source, and you can deploy any web application based on Java EE and experiment with what's available there. And this is what is available in Pyara. It's just two qualifiers, but they are very powerful. if you annotate an event with outbound qualifier, the runtime will automatically send the event to all the instances in the cluster. And the cluster is based on Hazelcast distributed memory and Hazelcast distributed queues. It's a library that supports auto detection of all the instances on the network, and basically can ensure that the messages you send to it are consumed by all the instances there. And in Paya server integrates this Hazelcast and uses it to transfer the messages. So all you need to do is put outbound annotation on the event, and on another application, we just need to observe the event with inbound annotation. So this is a small extension on top of a standard API in CDI events. And with this small enhancement, we can do something like this. In the previous step, we were sending whole response during a second channel to the WebSocket. Now, as I explained, it's better to send only chunks of data, stream of data, so that users know that something is going on, but also get the data as soon as possible, so that they can react before waiting for all the computation to be finished. And to do this, you have to get the messages from the service asynchronously, not only get the whole response with the REST call, but to change REST call to something else, because REST call always waits for the messages. There's one option you can enhance the REST call, and that's with service and events. So you change the REST call to normal HTTP call and enriched with service and events, so that server can send events to your client. This is possible with Java EE API in Java EE 8 version, which was released just a couple of weeks ago. But if you have Java EE 7, you may think that it's more of an overhead to change this and introduce some other library which is not available in the runtime. And one of the solutions might be to change REST invocations to CDI events, so that instead of sending a REST call, you wrap your object as a CDI event and trigger the event. And then you get two things. One of them is a synchronicity, that you can get back another event, which is a response type of event, and you can measure them together and continue processing. Another thing is scalability, so that the service that provides data can be scaled multiple times, and you can get events from all of them. So if they can communicate with each other and synchronize computation, you can compute all the routes in parallel and get the data much faster than if they were just computed by one single service. And this is just a configuration detail in the infrastructure. When you start more instances in the code, it's very simple to achieve that with just a couple of lines of code. With these two annotations and also synchronization of these services using JCache, which is also in Pyra server. It also is powered by the Hazelcast, and it provides distributed logs. So no longer messages are distributed, but you can also use distributed logs to somehow synchronize across messages, across services. So the third example is what we get with this approach, and it seems like the first example, but then the results of computations come one by one, and you can immediately react to it and click on one of them. So I hope you get where we understand where we got to. This obviously requires some changes on the front end, because previously it was a static application based on JSF. Now it has to be enriched by some JavaScript to be able to process WebSocket events. But apart from that, in the Java code, it's quite simple. It's just sending events instead of creating REST call. I can show you in an example. The ID has failed me. I'll show you later because I need to restart my ID. So I'll continue, maybe I'll continue with another step and then I'll come back to the code later. So now we're getting into more complex stuff. This was like a happy path where we improved our application, but the world is not simple. And usually when we start with already created applications, things are even more complex than if we start with a green application from scratch. And one of the complexities I already envisioned is when we have some calls, some parts of code which is inherently blocking. It's either impossible to rewrite it because there's no asynchronous API, or rewriting it would be very, very expensive because it would be lots of refactoring. And if you don't need to make this code efficient, you only want to focus on one part of application and the rest is okay, well, fairly well. One way of one thing you have to do is to isolate this reactive pipeline from the rest of blocking code. The reason for it is that the reactive pipeline really relies on making short tasks which don't block, and then you can make the thread pool small so that there's not too much jumping between these threads. It saves CPU because every context switch stops the CPU for a while until another thread is started or resumed. And any task that takes too long would again cause the thread starvation I was talking about before. So to avoid thread starvation, it's good to isolate these fast threads which process just small chunks which don't block, and when there is a blocking call, it's asynchronous. And if you don't have an option of calling something asynchronously, so that you can continue execution of some other task, then you should pass it to a different thread pool. And this thread pool can be pretty big, but it wouldn't be used so often because it's only for blocking tasks. So a blocking task is executed, the thread is put to sleep, then the blocking task is finished, the operating system will wake up the thread, and there's not so much context switching. In Java EE, to do that, you can use multiple executors. So there is a default executor if you inject managed executor service or if you use a synchronous annotation on EJB. But you can specify another executor in WebXML, you just give it the name. And then in the application server, you can configure the number of threads, but you can also predefine it in the application configuration in the WebXML too. Then in the code, you just need to inject a different managed executor and choose which one you need. So let me show you the code now. What happened? And get to the code. So I'll go to GitHub. So first I want to show you what I did to turn the REST call into CDI events. And basically I created another resource which I can use then as a REST resource, and which covers all the complexity. And now the code, instead of creating a web client for JAX-RS with a specified URL, I just use the the resource, call the get method, which is my implementation, and the get method will return the completable completion stage. And then there is the code which I had there before. So this is quite simple, but the complexity is how to get it is in this resource. And it's not so complex, but maybe when you look at it first, it may be complex. It's a couple of code, but what it does is it handles two events. One is to start a computation, and another type of event is the chunk of data that was computed. So one goes there to the computation service, another event and multiple events come back from the computation service, so that the main application can react to it and display the data. And to trigger a request, we just use the CDI event request with this outbound notation. Just for testing purposes now, I'm using this loopback so that I don't need to send it to another service. It also works if I deploy the service on the same server, but this is not mostly what it needs in production, because we run the service in a different virtual machine. And then what happens there is observer of a different type. So first I'm throwing events of graph traversal request, which is just a data transfer objects. It contains only the data necessary for the computation service to start. So it's basically the same data as sent through the REST call. All the parameters are in the object. And on the other side, we observe for events of type graph traversal response. And graph traversal is our service which traverses the graph of all the locations and connections between them and gives us all possible routes within among two locations. There's some more processing to turn this event into completable future or completion stage. So there's some logic. If the event is a termination event, it contains Boolean that our application detects. If it's a termination event, it will complete the completion stage with item processed and with processing finished. And if it's not a termination, it will just send item processed. This is a code which uses completion stage behind the scenes, because one of the disadvantages of completion stage is it's only one time stage. You can create a pipeline and then you finish the completion, completable future, and the pipeline is executed and that's done. You have to recreate the pipeline again. So I created another wrapper around this so that you can complete the future multiple times, and every time for a new event the pipeline is finished. You get that out of the box, as I said, with other libraries which make that much easier to do, like RxJava, where you create an observer and it observes for every event coming from a resource. That's out of the box. It's not supported by Computable Future, but it is supported by the new Java 9 Flow API. And when I said I want to use these thread pools, workers, executed services, I need to go to the itinerary selection, I think. No, it was Source itinerary. What was this? Where am I? Sorry, I'll continue. I wanted to show you how you can inject another managed executor and use it with completable future. Just to wrap it up, completable future also has variations of then accept and then consume, all the methods you can pass a callback to, and it accepts executor so that you can instruct it to run the callback in a different thread using this executor. Normally, it would just fork join pool, which in application servers context, when you want to access managed resources, is not a good option, because then no injection works, no JNDI lookups works. You need to somehow make this work in the code. There's a possibility to use context service, but it's very cumbersome to do. So if you pass a managed executor received from the application server, then all of this works out of the box. And the last thing is context propagation, which is a thing that may surprise you when you try to improve your application. Everything works until something stops working suddenly. And the problem is that sometimes the context is bound to the thread, which in reactive programming is there's not an option. If you execute your code in a different thread and one request is executed across multiple threads, every time jumping to another thread, you have to take the context, all of the context with you, with the execution to the thread that's executing it. So if there is some context bound to thread, for example, in Java EE, there may be some CDI context like request context bound to a thread, then you may have a problem and you need to get all the data and put it to a different thread. Another problematic resource is transactions. Transactions, at least in Java EE application servers, they are bound again to the threads. The JTA specification says that they are bound to the thread, and there's a way around it, but not standard. You have to receive a transaction manager, which is available in most of the application servers, but that's not prescribed by the specification. So it may work on some application servers. On some application servers, you need to use a different code, different method to suspend the transaction and move it to another thread where you can resume it to process the execution in the same transaction. And you also need to transfer the security context, the user that is running the code, the principal, so that the code in another thread knows of a current user and all the security constraints can be applied against this user, not against an anonymous user. There are some solutions to these problems, as I explained. You can find a way how to suspend a transaction using Transaction Manager. For CDI scopes, there are request scope and session scope that are specifically bound to a thread. So if you really depend on these scopes, you should rework your beans in the application, the dependency injection configuration to use different scope, custom scope, which will start with the request, but will not end with when the thread completes the request, but when the request is really completed by sending the data to the browser. And to simplify this, there's a project called Microscoped on GitHub, which is an abstract context which you can reuse and specify the boundaries of the context, because normally in CDI you can create an extension, but the API provided by the extension is quite complex, and this project makes it much simpler to build external a custom scope. And then instead of add request scoped, add session scoped, you use your custom contexts which resemble these but are not bound to the thread. To sum up, you see that reactive programming is not an easy thing to do. It's more for cases when you really want to optimize your applications or build really highly optimized applications from scratch. There are frameworks that focus on this style of programming to make it more simple. But the downside is that when you start with these frameworks, you very often have to continue with this in every part of your application. And maybe not a whole application needs to be optimized this way. And then there's the disadvantage of slower developing of the code, because you have to think asynchronously, you have more things to think about. One of them is when the asynchronous call finishes. What happens if it doesn't finish? You don't get that in a blocking call, because when there is an error, you get an exception, and you wait for either exception or a result. With asynchronous call, you just trigger an event or trigger a call and wait. And what happens if nothing comes? So you have to consider all these cases, and it's quite easy to miss them. I think I have time for some questions. If you have some, I have also some T-shirts. So if you raise questions, I can give it to you as a prize or for me. Okay, so maybe you have some questions later. So come back to me. I have Pyara T-shirt on me. I have also some T-shirts from my company, Pyara, and yeah. Thank you for attention.